In this video, you will learn about adding vectors. First of all, you'll notice I have 3 vectors on the screen here. Would I be able to add the green and the blue vector? If you answered no, you're absolutely correct. I cannot add the green and the blue vector because they have different units. The first important fact is that you must have the same units to be able to add vectors. What about the green and the pink vector? Could I just add those by simply adding 5 plus 3? If you answered no, you are correct again. You must pay attention to the direction of vectors as well as the magnitude when adding them. We'll learn in a few minutes how to add the green and the pink vectors. But before we do, there's an important term that you must know that relates to adding vectors, and that's the term resultant vector. A resultant vector is what you get when you add 2 vectors together. Now that we know some of the terminology and the basics of adding vectors, let's actually add a few vectors together. We're going to start with the simplest case, which is when vectors are parallel to each other. You'll see I have several vectors here that are all parallel to each other. We're going to look at adding those together. The simplest format is when you have 2 vectors that are going in the exact same direction, like the green and the blue vectors you see here. If vectors are going in the exact same direction, you can simply add their magnitudes together. Now you'll see that this is titled Adding Vectors Graphically. And that's because we're going to go through a format of what you do when you add vectors graphically. Specifically, when you're adding vectors graphically, you want to draw the 2 vectors so that they are tip to tail. Okay, what exactly does that mean? Well, let's say I have 2 vectors, the green and the blue vector again, for example. If I were to draw these 2 vectors tip to tail, that would mean one of those vectors would look like this, and then the other vector would look something like this. Now, putting them tip to tail means that I take one of those vectors and move it so that its tail is at the tip of the other. Then I can see that my resultant vector is this entire length here. So if I add 5 and 2, I get the magnitude of my resultant, which would be 7. Now, if I have vectors that are in opposite directions, let's say this blue vector all of a sudden goes in the opposite direction, and I place those tip to tail again. Well, now you can see that my resultant vector would be a lot shorter. When I have vectors that are in the exact opposite direction, I can still put them tip to tail to add them graphically, except this time they end up going in opposite directions and their magnitudes subtract instead of add. What would I get if I added the black and the green vectors? If you answered that my resultant would be 2 units up, you are correct. Similarly, if I added the pink and the blue vectors, my resultant would be 2 units, but in the downward direction this time. Now, our vectors are not always parallel. Sometimes they're perpendicular. When it's the case that my vectors are perpendicular, putting them tip to tail is even more important. Let's say, for example, that I was adding the purple and the blue vectors together. I would need to put those 2 vectors tip to tail. In other words, if I were drawing a picture of the 2 vectors, that would be my 5 unit purple vector, and this would be my 3 unit blue vector, so that my resultant would look something like this. The resultant will always start at the tail that's all by itself and end at the tip that's all by itself, so that we get 2 tails together and 2 tips together. Now, I could have added those in a different direction. In other words, I could have done 3 like this, and then 5 like that. I would still get the exact same resultant as what I had before. So it doesn't matter which tip goes with which tail. Okay, let's actually try this out now. As you see here, this problem says, while following the directions on a treasure map, a pirate walks 45 meters north and then turns and walks 7.5 meters east. We want to know what single straight line displacement could the pirate have taken to reach the treasure. This is a problem that is giving us some context, but basically is asking us to add together these two perpendicular vectors. Since we're talking about adding vectors graphically, we're going to draw a picture to start off. It's important when you draw your picture that the vectors be somewhat relative in length. In other words, 45 meters north should be much longer than 7.5 meters east. So I've got a vector, 45 meters north, and another vector, 7.5 meters east. I'm trying to add these two vectors together, and you'll notice that I've placed them tip to tail, so that my resultant vector starts at the bottom of that 45 meter vector and goes up to the tip of the 7.5 meter vector. This is my displacement vector. Now, to add these two together, you'll notice that they make a right triangle, because that 45 meters is a right triangle with the 7.5 meters. So, if we're trying to find the magnitude of my resultant vector, the Pythagorean theorem is the best thing to use. The magnitude delta x is equal to the square root of 45 meters squared plus 7.5 meters squared. That yields a magnitude of 45.6 meters. Now, we know that displacement is a vector, which means that we not only need a magnitude, but we also need a direction. Here's an important fact. The angle that you are finding when you're finding direction is always the angle that is at the base of your resultant vector. That means we have two options for an angle here. I'm going to start out by drawing an xy axis at the base of this triangle, at the base of my vector basically. So there's my xy axis. Again, two angles that I could find. I could find this very small angle that is within the triangle, or I could find this much larger angle that's with respect to the x-axis. I personally think it's easier to find the one that's in the triangle because it's really obvious that I can use a trig function to do so. Since I know all three sides of the triangle, I could use any trig function I would like, but I always prefer to use tangent since the x and y components were the things given to us. So, the tangent of the angle I'm looking for, I'll call that theta, is equal to opposite over adjacent, or 7.5 meters divided by 45 meters. Now, of course, what we're really trying to find is theta itself. So to find theta, I'll use the inverse tangent of 7.5 meters divided by 45 meters. This gives me a value for theta of 9.46 degrees. Now, once again, we learned in class that it's not enough to just give an angle, we have to tell where as well. So the full and complete answer for this problem would be that my displacement is equal to 45.6 meters at an angle of 9.46 degrees, and I would say east of north. Again, I tend to prefer using the north, south, east, west notation. Other ways that I could have represented this angle is I could say that it's 9.46 degrees to the right of the positive y-axis, or if I had found the complement to that angle, that's the bigger one that you see, which ends up being 80.54 degrees. I could say 80.54 degrees north of east, or 80.54 degrees above the positive x-axis, or 80.54 degrees ISP. Lots of options there. Now let's look at an example for adding parallel vectors. In this problem, we're looking at two vectors, A and B. It says vector A has a magnitude of 29 units and points in the positive y direction. So vector A looks something like this. When vector B is added to A, the resultant points in the negative y direction and has a magnitude of 14 units. So it would be about half as long as that, and pointing downward instead of up. It's asking us to find the magnitude and direction of B. Well, first of all, you should be able to figure out that our unknown B has to be something in the y direction, either up or down. Otherwise, my resultant would have an x component, which it does not. Adding vectors graphically is the best way to solve a problem like this. So in other words, what I'm trying to do is to put A, the 29 unit vector, plus B, my unknown vector, tip to tail, so that the resultant ends up going tail to tail and tip to tip. Okay, here's what that means. So let's redraw these two vectors so that they would be in the correct orientation to add them graphically. I'll start off with my 29 unit vector. And then I eventually need it so that my 14 unit vector would match up with this tail. And we'll see what the tip ends up looking like. So here's the 14 unit vector. And then B, my unknown, would have to have its tail on the tip of the 29 unit vector and its tip where the tip of the 14 unit vector goes. So you can see that B is downward. And if I think about magnitudes, this is 29 and this is 14. So that means that B must be equal to 43 units, and its direction is downward. Hopefully the process of adding parallel and perpendicular vectors is a little bit more clear to you after this video. So now it's your turn. In this example, we're given two displacements, and your task is to find the total displacement. Make sure you show your work and bring this to class with you the next time we meet.